All right, how's it going, everybody? We are here. I'm making this video today on Wednesday, April 21st, and today we are going to celebrate the end of Chapter 3, and we are going to celebrate it by continuing on with the exact same topics in Chapter 5 right here. So in Chapter 3, we just did a whole mountain of work to classify the behavior of linear systems of differential equations near the equilibrium point at the origin. That's a super, super specific thing that we've been working on, and I think chapter 3 is really hard. There's a lot of work, there's a lot of math that went into that, and it was to classify a bunch of like very, very particular scenarios. What our goal for the rest of the semester is going to be is we're going to take a quick lap around chapters 4, 5, and 6, slightly out of order, to look at saying, can we expand on chapter 3? Can we cover, can we like apply our concepts from chapter 3 to a much broader set of scenarios? This seems, chapter 3 was so specific that chapter 3 alone isn't really useful. What we want to do is we want to say, what if our systems are nonlinear? What if we write differential equations that actually do have a t term within them, a second order differential equation that's not autonomous? Um, what happens if we can't go the linear algebra route and we need a more powerful calculus tool? What we want to do, looking at the rest of the class, and by the way, you can see pretty much the entire rest of the class above my head right there, is that we're going to look today at equilibrium point analysis and linearization. That's section 5.1. And we're doing chapter 5 next, just because this extends on very, very smoothly from chapter 3. Then in chapter 4, we're going to go back to look at more of our second order differential equations, and we're going to say, what happens if there's some other terms floating around in our second order differential equations other than just a coefficient on x double prime, a coefficient on x prime, and a coefficient on x that are all constants? Maybe we've got some more exciting things going on in second order differential equation. We're going to look and see how we're going to deal with more terms being in there in chapter 4. Finally, in chapter 6, we're going to say, all right, so we need a more powerful calculus tool that's going to help us do calculus that otherwise would be too difficult for us to do. We're going to convert calculus problems into algebra problems in chapter 6, solve the algebra problems, and then convert back to the calculus problem with some Laplace transforms, which is the sibling of the Fourier transform, which we'll briefly mention in there as well. So we're going to take a hot lap around chapters 5, then 4, then 6 to wrap up this class here. So today we're talking 5.1. So today's goal is to say, how much information can we really get about a system by only looking at the math that we did in chapter 3? And the answer is, if you have a system that isn't just a linear system, ax plus by and cx plus dy being your two differential equations, then it might be that you have equilibria at places that aren't the origin, and therefore it seems like they might be interacting with one another in such a way that it doesn't seem necessarily appropriate to just say, in this picture, you're going to see a spiral source. If there's multiple equilibria and only one of them is a spiral source, how are they going to interact with one another? And we're going to see that answers that's going to be a kind of a tough one to answer right there. But again, the point stands that says, what if we have more than one equilibria, and what if those equilibria aren't at the origin? How do we deal with classification of things that aren't at 0, 0? That was a very important part of everything happening in chapter 3, that all the behavior was near the origin that we've been describing. So let's go ahead and take a look at what's going on here in section 5.1, equilibrium analysis, equilibrium point analysis and linearization. And we're going to see a bunch of cool examples today. We're going to see that we can extend our math not too terribly difficultly from chapter 3. We're going to see a bunch of really cool pictures today, a lot more exciting phase diagrams than I think we've seen in a while. So let's start with one example, and all we're trying to see in this example, so our first example is we're going to look at the van der Pol equation. The van der Pol equation is really a second order differential equation, but our second order differential equations we can always convert to a system of first order differential equations, as we've done many times. And so all I want to ask here is, I'm not even worried about equilibria at places other than the origin, where this one only does have an equilibria only at the origin, so that's not the exciting point of today. But the point is, can we classify the behavior near the origin, even though this is clearly a non-linear system now? And if we can classify the behavior at the origin, do we feel like that's fully representative of the descriptor of what we're going to see in the phase plane out here? Or is that now maybe less of an overall good description right here? So the first thing that I'm thinking to myself right here is that this first differential equation doesn't seem to be problematic to me, but this second one is, because this is not linear, right? So I'm going to say here, this is a linear differential equation. This is a not linear differential equation here. So I'm going to kind of expand this guy a little bit, right? This is negative x plus y minus x squared y. And what I'm thinking to myself is this. Near 0, 0, this term is way smaller than the other terms. Right? And just think about if x and y are zero point 0.1 each, if that's our initial condition. Well, then dx dt is going to be equal to 0.1. dy dt is going to be negative 0.1. But this quantity over here, we're getting like a 0.1, or excuse me, this x squared times y right here, that's going to be 0.1 cubed. That's going to be 0.001 right there, right? So that's a much, much, much smaller contribution to the overall value of dy dt and then the negative x and the positive y are contributing right there. So kind of the point here is to say, if I wanted to sort of make an estimate of what this system is sort of like, then we could say that we could linearize the system by neglecting higher order terms. And that's to say, listen, some of these terms near the equilibria of interest are going to have such smaller values than the other terms that it might be reasonable for us to estimate that it's okay to just ignore them because they're going to be so close to zero. So to linearize this system, I would rewrite it as dx dt equals y and as dy dt as certainly approximately being just negative x plus y, right? Because these terms near 0, 0 are so much smaller than what these terms would be because we're essentially, you should think of this as being like a cubic. All right, there's three total variables being multiplied together. If x and y are both near 0, this is basically like a cubed function that's near 0, so it's going to be incredibly, incredibly small. So what we can see from this guy right here is we could form our general coefficient matrix of 0, 1, negative 1, 1. And what we learned from our trace determinant plane is that we could take this A matrix of 0, 1, negative 1, and 1. I could compute my trace and my determinant. My trace is the sum of the main diagonal, it's 1. My determinant is 0 minus negative 1, which is positive 1. And so I'm going to get t squared minus 4d is going to be equal to 1 squared minus 4, which is less than 0, so we're complex. So I know we're getting a spiral sink, a spiral source, or a center. Based on the fact that my t value is positive, and I know that my lambda looks like t plus or minus the square root of t squared minus 4d all over 2. Since t is positive, I'm thinking that this should be like a spiral source. So this is our very first look at a non-linear um, system of differential equations. And essentially all we're suggesting here is that and now here's the super important part. The only reason why this was legit is because we were looking at an equilibria that was near 0, 0. If this equilibria were near 5, 5, then you should notice that this cubic term would all of a sudden become the most dominant term. And in fact, we would probably discard the smaller terms over here, these lower order terms. If we're looking at the equilibria being near 5, 5, then these values are going to be something like 5 cubed. That's going to be like 125 versus these values just being like 5. And all of a sudden the x and the y are representing, 1/25th of what the x squared y term is actually representing right there. So the important thing for this linearization is it only made sense for us to neglect these higher order terms, to just straight up discard them because of the fact that we are near 0, 0. So this near 0, 0 thing is really important. It's not just that 0, 0 was the equilibria, it's that literally the number 0 is different than other numbers in that it's the number that represents no contribution to the overall quantity of interest here. So because the equilibrium was near the origin and because we wanted to know the behavior near the origin right here, it is mostly mathematically acceptable for us to approximate that this system should mostly look like this linearized system over here, as long as we're only saying this is our description of the system near the origin. So linearization of the system near 0, 0 only, right? Far away, I don't expect this to be a good descriptor of my system because far away from or the origin, the x squared times y term is going to make a hugely meaningful contribution to what dy dt is doing. But near 0, 0, it's really not. So near 0, 0, this is a good approximation of what our system should look like. So near 0, 0, I'm expecting to see a spiral source. So what I now want to go do is let's use some technology to go take a look and see, do we see a spiral source here? To what degree do we think this linearization was a good idea? To what degree do we think it was a bad idea? Let's take a look at a picture to help us sort of answer that question for ourselves right here. So what I'm going to do is I'm going to go to our Python grapher over here. So here's our Python grapher, the general system grapher that I shared with you guys. And so here's what I'm going to do. And let's maybe just to kind of refresh this here. Let's restart and clear all output. There we go. We're restarted here. It's got no numbers over here. So I'm going to run my library imports. I want to show you that I've set up something ever so slightly differently here. So defining the differential equations. When I originally gave this to you guys, I gave the A, B, C, D. And I gave you these definitions for our linear system. Clearly our ax plus by, cx plus dy. We're no longer in our linear system land, so this is no longer helpful for me. So I'm going to go ahead and comment this stuff out right there because that's no longer a good representative of the system I'm trying to describe. Instead, I'm going to define the system associated with the van der Pol equation. So I've got just new definitions for f and g set up for myself right there. By the way, we're going to see another example later, so I've already got that guy sitting right there. So this is just me saying I've got a whole bunch of different options for what I want to define my system to look like right here. Since we're no longer in linear systems, I've just got a bunch of them typed out, and these two, you can see the top and bottom are commented out, so they're not getting run. This middle one is the only code that's actually going to end up getting run right there. And I'm still leaving my standard initial condition list that we had before, but I'll show you for a problem later. I'm going to want to beef up my initial condition list, but that'll come in our later problem. So I'm going to run this. So I've got my van der Pol equations here. And I think I'm leaving this at the same settings that I've been leaving this at before right there. I don't see any reason to do anything much more than that. So I'm going to run all the code right here, and let's see what our plot looks like. All right, so here's the graph that I'm seeing. And so I think one thing I want to do is I want to modify the viewing window real quick here. It looks like maybe my x values can go from like -3 to 3, and y from -3 to 3 is maybe our better viewing window right here. So I'm going to do this. I'm saving these so that I can switch back to this viewing window later. I like to leave lots of just like commented out blocks of code that I might want to switch to later. Now I just have to delete the comment and re-comment something else, and I've got a new window for viewing this. So here's what I'm seeing for our overall system behavior, and I'm not too worried about this kind of mess down here. This is going to be tough to interpret with too many initial conditions, but here's what I'm seeing. One, from all of these initial conditions, it seems like our solid lines are moving outward. So I do see this spiral source type behavior from all of our initial conditions. I'm noticing that in backwards time is where we're spiraling in. So that says in reverse time, it's a spiral sink, which means in forwards time, it's a spiral source. So I am seeing this spiral source type behavior around the origin. However, what we're noticing in this one is it doesn't seem to just be spiraling outwards forever, but I'm a little bit suspicious. I mean, is this maybe spiraling out forever? Maybe we should just graph this for longer. I think that we're just graphing this for too short of a period of time. So I'm going to extend my time final to 10. So this just says, just keep on graphing for 5 additional seconds, twice as long as we were before, and let's see what our new graph looks like. So what I'm seeing here is having graphed this for twice the duration of time, I don't see like any new like expansion out into space. It seems like we are spiraling outwards at first, but then it seems like we are meeting some sort of odd-shaped boundary out here where we're no longer spiraling outwards later. All right. So what this says to me is, I think our linearization was good, right? If you go ahead and look at the graph through your little pinhole right here, and you only look near the origin, if you're only looking near the origin through your little peephole here, this is totally just a spiral source, totally. However, we're seeing as we get farther away from the origin, our linearization that it's a spiral source is no longer a good descriptor of what's going on far away from the origin. So it seems like our linearization did exactly what it was supposed to. It did do a good job of describing the information of the system locally because it was a local linearization. Far away from the equilibrium, places where it was a bad approximation for us to ditch those higher order terms, the spiral source is no longer a good description of what we're seeing in the system out here, right? So let me snag this picture and throw this. I want to put this in. Oh, wait, I keep forgetting. I keep on going to take screenshots of this, and I keep forgetting I can just copy and paste. Copy, and let's bring this guy over here. So this is our first little lesson of the day, is that linearization seems to be a relatively reasonable thing to do. as long as we understand that those descriptions that we're coming up with are only good locally. If we are coming up with a local linearization, it's only good for a nearby area that's a good descriptor, and far away, probably a bad descriptor right there. So coming back over into Word here, I want to say, I just kind of want to conclude exactly what I just said. Um, the behavior does look like a spiral source near 0, 0. All right, so I think this did exactly what I thought it was going to do. We were sort of right to just ditch those higher order terms as long as we understood that we were only getting a description of what's going on near the origin when we did that type of linearization. So that's sort of lesson number one of the day is it seems like as long as as long as the equilibrium's at the origin, that's still like a kind of a firm requirement for this. Again, if that equilibrium was near 5, it wouldn't have made any sense to ditch these higher order terms. They would have been making massive contributions to the overall value of dy dt. So it seems like if the equilibria is near 0, 0, it's acceptable for us to just ditch higher ordered terms to linearize it and then to say, hey, here's my estimate of what we should expect to see near 0, 0 only, right? Spiral source. So our next question should be, well, what if our equilibria aren't near the origin? That's really our issue here. This whole thing that we did was very dependent on this equilibrium actually being at 0, 0. That was a necessity here. So the question is, how do we handle this same type of concept if we're not near 0, 0? So let's go ahead and step up our example now and say, let's look at a new setup here where we're going to get some other equilibria, and then we're going to ask, and you can see the bottom down here. So the question at the bottom, how do we classify equilibria that are not at the origin? So let's go ahead and look at this nonlinear system right here, and let's find all the equilibria. Let's with the equilibria, let's at least try to start drawing our overall phase diagram by at least just drawing the phase lines that are associated with the x and the y axis. I want to point out that even though this is exclusively an algebra problem, I would go so far as to say that most differential equation students struggle solving these systems of equations right here, and I get why. I sometimes get a little bit lost myself. So what I know I need to do is I know that I need to set dx dt and dy dt equal to 0. So equilibria are going to occur where dx dt equals dy dt equals 0. Right? I know that's my goal, is to have both dx dt and dy dt be equal to 0. I know all xy pairs are going to do that for myself. Now, when I'm trying to solve equations being equal to 0, I know that I like factored form better than I like some expanded standard form. That subtraction sign is sort of like my least favorite part about this. So the thing that I'm thinking to myself is this first term has an x in it, and the second term has an x in it. So let's go ahead and factor out that x. And what that should leave me with is 2 times 1 is 2. 2 times negative x over 2 is just negative x. And the remaining term over here was a y. So this is going to be a much better form for me to set this equal to 0 and solve. Let's do the same thing on the second line. First term is a y, second term has a y. So I'm going to factor out the y, and I'm going to push the 3 through the fraction here. So that's going to give me 3 minus y. And then left over, having factored out the y on the back term here, I'm going to get a minus 2x, right? So I just think that factored form is better for me because of the fact that I'm trying to set equal to 0 and solve. Factored form is going to be my friend. So I'm going to set up these two equations here then. We're going to do x times 2 minus x minus y equals 0. And you should notice that, so I'm going to kind of solve these one by one. So this says to me, either we're going to get that x equals 0, or we're going to get 2 minus x minus y is equal to 0, which I might rewrite as y equals 2 minus x. These are the two sort of cases that I came up with from setting dx dt equal to 0. Now I'm going to come on over to dy dt equals 0. equals y times 3 minus y minus 2x. And the first thing I'm thinking to myself is, well, what happens when x is equal to 0? If x is equal to 0, because I know that that's one of the ways that I get dx dt to be equal to 0, if x is equal to 0, then we're getting y times 3 minus y equals 0. And that's going to lead me to y equals 0 and y equals 3. And so therefore, I know from this guy now that I have got the solutions of 0, 0, and 0, 3. So I've got two equilibria here. So again, notice what happened here. I let x be equal to 0 because if x is 0, then the whole dx dt equation is equal to 0. X being equal to 0 led me to realize that we could either have y equal to 0 or y equal to 3 to make dy dt be equal to 0. So therefore, x being 0 and y being 0 works. X being 0 and y being 3 works. And so we've handled the x equals 0 case here. Now I want to say, what happens if y is equal to 2 minus x? And we should notice that y could be equal to 0 here instead. Then we're going to get 2 minus x times 3 minus 2 minus x minus 2x equals 0. I'm going to get 2 minus x times 3 minus 2 is 1. That's a positive x and a negative 2x. So we're getting minus x equals 0. So it seems like we should be getting x equals 1 or 2. And you should notice in this equation right here that with y equals 2 minus x, that should be leading us to be paired with, it looks like we're going to get x being 1 makes y be equal to 1. Or if x is 2, then it looks like we're going to get y equals 0. So it looks like I've found some more here. And finally, you should notice that another case that should have come out of here is the y being equal to 0 case. And you should notice that if y is equal to 0, then that's going to require that x is either, so if y is 0 over here, then dy dt is equal to 0. And if y is 0 over here, then we either need x to be 0 or x to be 2. Well, if y is 0 and x is 0, we already covered that one. If y is 0 and x is 2, we've already covered that one. So it seems to me like I think that I got all of my possible equilibria that are out here. I think these four are going to represent all of them here. And what I'd like to do is I'd like to draw phase lines to kind of like get my picture going, basically, is what I'm saying. So what I'm seeing here is this. It seems to me like we should be getting, and I'm just going to draw my first quadrant, by the way. Like we should be getting an equilibria at 0, 0. We should be getting one at 0, 3. That's going to be way up here. We should be getting one at 2, 0. That's over here. And we should be getting one right here at 1, 1. And my question is, what do we think our graph really looks like in general here? Well, I'm noticing here that these phase lines could be made up. We could think about phase lines here for the x and for the y axis here. And so I'm just thinking here, if y equals 0, then we're on the x-axis. And if y is equal to 0, I want to know in what direction is x changing here. So we're going to see dx dt equals x times 2 minus x, right? Because the y component is 0. We just said that right there. So it seems to me, like based on this equation right here, that 0 and 2 are the two equilibria. It seems to me like if I plug in, for example, the number 1, we're getting a positive times a negative, so we're going left. If I plug in a number like 3, we're getting... Oh, wait, sorry. No, that was a lie right there. I was seeing x minus 2. If I plug in a number like 1, we're getting 1 times 1, which is positive. I'm seeing that if we're plugging a number like 3, we're getting a positive times a negative, so that's a negative. I'm seeing that if we're plugging in numbers like, oh wait, I don't even care because I'm only thinking first quadrant stuff. So I think that I can go ahead and confidently place these arrows here. And similarly, if x equals 0, the y-axis, then I want to ask what's happening with my dy dt here. What's our rate of change vertically on the y-axis right here? Then dy dt should be equal to y times 3 minus y. And so we're going to get basically the exact same type of picture right here. Again, if I plug in 1, I'm getting 1 times 2, so that's a positive number. We're moving to the right. If I plug in 4, we're getting a negative for the second term, moving left. I don't care about the other side. So it seems like this is moving in these directions here. So the bottom line is I kind of actually have a decent idea of what I think the phase diagram looks like right here, sort of. I think I know at least of what's going on in the axes. It seems like the origin, 0, 0, is probably a source. It seems like this is maybe a sink right here. What else could this be? Does this have to be a sink at 0, 3 and at 2, 0? I think that this could potentially be a saddle where we have another line that's moving outwards through that point. I also think that this could be a degenerate sink right here where this is our one line of equilibrium and things are trying to spiral near towards it. But these are just guesses that I'm making. I have no idea how to make the guess about what's happening at 1, 1. All right, so see here that we can find the equilibria. We can draw some parts of our phase diagram by hand, but we kind of get stuck here because of the fact that we can't, that this isn't a linear system, so we don't have a way to do the classification yet, right? Now, I want to go show one thing real quick, and that is that I am assuming that some of you just did not follow along with the algebra that I did here. So I want to show you in Desmos a different way that I can go about solving this the system of differential equations here, because there's a little bit of a trick to it right here. So I'm going to pop over to Desmos, and I'm going to show you, based on these equations right here, what the right way and the wrong way is to use Desmos to help you find your equilibria right here, because this can be tricky just like the algebra is slightly tricky here. So here's what I'm going to go do. Over here in Desmos, what I want to do is I want to know when is it the case I want both of these equations to be equal to 0. So it should be the case that I should be able to throw this equation equal to 0 into Desmos, this equation equal to 0 into Desmos, and I should just be looking for intersections of those two lines. Watch and see what happens here and why. So I'm going to come over to Desmos and I'm going to type in these equations here. We had x times 2 minus x minus y equals 0. And I've got y times 3 minus y minus 2x equals 0. And you should notice that it kind of did something nice for us. I'm at least seeing out here, hey, I'm seeing 1s popping up, but I'm seeing, like, I don't know, like, why is it not even giving me a point right there for that one? I don't understand that one. So I feel like it's kind of doing some weird things to me where it's like, why is this a point that is on there? Why is Desmos not giving me this point? What's going on? Why do we not have anything at the origin? It doesn't seem like just straight up throwing your differential equations equal to 0 in here is very useful. So here's the smarter way to do this. What I know is that the zero product property tells me that if this equation is equal to 0, it's really that either x needs to be equal to 0 for dx dt to be equal to 0, or 2 minus x minus y needs to be equal to 0, so that dx dt is equal to 0. Same things can be said down here, but we're talking dy dt. So here's what I'm going to do. I'm going to make this its own separate equation. Make this x equals 0 its own separate deal right here. Similarly down here, I'm going to get rid of this y, and I'm going to make this a y equals 0. So this is really me like writing out the zero product property, right? Is the first factor is equal to 0 or the second factor is equal to 0 for both. So the good news and the bad news is that this now gave me the horizontal and vertical lines at x and y equal to 0, which should be there. But my issue is I don't know how these are related. And here's the important thing. Here's the really important thing. These first two equations here are deeply related in that these are the two ways that dx dt could be equal to 0. So what I'm seeing here, for example, at this point of 0, 2, at 0, 2, this is just the location where there's two different ways that dx dt is equal to 0 because it's on the green and the black curve, but there are no ways in which the dy dt is equal to 0. Right? That's so this doesn't turn out to be one of the places I'm looking for. So what I typically do here is this. I'm going to go to my colors in Desmos, and I'm going to pick some colors. So I'm going to make both of the top two equations green because these are the two equations that represent dx dt equal to 0. I'm going to make both of my bottom equations purple because they both represent the two equations where dy dt is equal to 0. And now what I see is that all of my equilibria are located at the intersection of a green line and a purple line because I need both dx dt equal to 0 and dy dt equal to 0, not something like dx dt equal to 0 twice. Right? So what I'm seeing here is green intersects purple is here, green intersects purple is here, green intersects purple is here, and green intersects purple is there. Those are the four places where we're finding equilibria on this guy right here. All right. So using Desmos here to help you, I would recommend one, try to get your differential equations into factored form. Two, write out every single individual equation associated with the zero product property that you get from each of those differential equations being set equal to zero, and color each term from the zero product property the same for each set of equations. The green stuff is my dx dt equal to zero, purple stuff is dy dt equal to zero. You are therefore looking for the intersection of any green line with any purple line. And there's our four solutions right there. That'll be very helpful for you in the homework this week, I believe. Okay, so now let's come back here and say, okay, so we found them. We can draw some light pieces of our phase diagram here, but we really don't know how to classify kind of any. We could probably do the one at the origin by doing like the stuff that we did above and neglect those higher order terms. But overall, like I don't see what we're going to do with our other three equilibria right here. So the question is, how do we classify equilibria that are not the origin? And you guys are all algebraist masters by now. And the answer is we're just going to move them to the origin. So what we're going to do here today is we're going to create new variables that are going to shift our entire system so that an equilibria is at the origin. You should notice with this new system of variables right here with u and v, if we could rewrite our entire dx dt and dy dt differential equations in terms of u and v, it should be the case that notice, for example, the equilibria at 1, 1. Well, 1, 1 for xy means that uv has an equilibria at the origin. And origin equilibria we can always classify doing our linearization technique. So our big idea today is if you have an equilibria that's not at the origin, move it to the origin, then linearize by discarding all higher order terms, and go ahead and classify the equilibria. Now, what I just said is completely correct, but it's certainly an oversimplification of what we're about to do here. We want to come up with a kind of a good route to doing this rather than kind of redoing all the work by hand over and over again. So we should notice here that when we do u being x minus 1, then I'm seeing here things like du dt equals the derivative with respect to t of x minus 1. And that's just going to be dx dt. So I'm seeing that du dt is dx dt, and similar, dv dt is equal to dy dt. So those just get swapped out directly. I think I want to copy and paste these. Well, okay. I'm going to... Okay, yeah, sorry, I was just double checking what we're doing right here. So what I'd like to do is it's not going to let me do it. So x times 2 minus x minus y x times 2 minus x minus y. And so I'm going to convert this one into u's and v's, and we also got dy dt was y times 3 minus x minus 2y, I believe. 3 minus x minus 2y. 3 minus y minus 2x. So let's go ahead and convert these guys using our substitution, then linearize, then classify, right? So converting. Well, one thing I see, dx dt is literally the same thing as du dt because we only performed a shift, so our derivatives stay the same. It seems to me like it's also going to be very, very helpful for me to write these things as like u plus 1 equals x and v plus 1 equals y. So x is u plus 1 times 2 minus u plus 1 minus v plus 1. Right? And if I expand this a little bit, I'm going to get u plus 1 times, let's see, 2 minus 1 minus 1. So all the constant stuff is gone. Here I'm getting a negative u and a negative v. So it looks like I'm getting here something like a du dt equals, and it looks like here I could expand this to be like a negative u squared, a negative u, and then a negative uv, and a negative v. So there's one of my differential equations there. du dt equals that guy. Let's do the exact same thing here for dy dt. dy dt I know is equal to dv dt since it was just a constant shift. Y is equal to v plus 1 times 3 minus y is v plus 1 minus 2 times u plus 1 is what x is there. And therefore we're going to get dv dt equals v plus 1 times, I've got 3 minus 1 minus 2, so all the constants cancel. I'm getting a negative v here. I'm getting a negative 2u here. So I could rewrite this as negative v squared minus v minus 2uv minus 2u. So here is my new system right here, converted into u and to v. So that's step one. Now what I'd like to do is I'd like to recognize that there is the equilibria at xy equals 1, 1 is now at uv equals 0, 0. You should very quickly notice that if we make u and v both equal to 0, then we are definitely getting du dt and dv dt both equal to 0. So it does seem like we did correctly shift the 1, 1 equilibria to being at 0, 0. So now we can linearize by neglecting higher order terms. Remember, this close to 0 matters because when you square a number or cube a number that's near 0, it gets much, much smaller, right? And so those are going to be much, much smaller in size than other things. We are just looking for a local linearization then. So we say that du dt, I'm going to neglect higher order terms. It looks like it's just negative u minus v. And dv dt seems like it should be, I'm going to neglect higher order terms, and I'm going to get negative 2u minus v, right? The higher order terms like uv and v squared and uv and u squared are all those higher order terms that we're neglecting. This is going to lead us to having this coefficient matrix A that looks like negative 1, negative 1, negative 2, negative 1. And I can compute my trace to be negative 2. I can compute my determinant to be what? 1 minus 2 is negative 1. And so right away, right there, I can see that we're going to get a saddle because we had a negative determinant right there. Anytime the determinant is negative, we're on the bottom half of the trace determinant plane right there, and therefore it looks like we should have a saddle at. And now I'm thinking at uv equals 0, 0, but that should be telling me we should be having a saddle at xy being equal to 1, 1. That's the thing I think I'm trying to kind of take away from this guy right here. So it seems like we can do some of that classifying right here, right? So we did that. We did the convert to UV. We did the linearizing, and then we did the classifying right there based on the linearization, right? So what I want to go do is we should probably go take a peep at this thing using some technology to see if this does in fact look like what we're thinking we're seeing right here. For this particular one, just because I don't want to screw around with my initial conditions, I am going to go use Bluffton to look at this guy right here. But we'll use Python for most of the rest of the ones today here. So I've learned my lesson. I'm going to set this to RK4.01. I'm only really interested in, I guess I'll do it like this. I'm mostly interested in the first quadrant here. So I'm going to go like that, so that we're mostly just looking at the first quadrant. Oh, I'm changing. Oh no, okay, kept all my settings. That's good. And so what do we have for our dx dt? Our original equation had dx dt being x times 2 minus x minus y, and then our dy dt had y times 3 minus y minus 2x. And when we do this, what we were thinking was that at 1, 1, we should have an equilibria. So I'm going to go put in my solution at 1, 1. And notice it didn't graph any curve because it just has a point that's sitting at 1, 1. What I really wanted to do is see what's going on around 1, 1. So I'm going to click on a bunch of curves near it. So this does look to me like the stuff I typically see in association with these saddles, right? I see things that look like we've got a sink line happening diagonally this way and a source line happening diagonally towards the other equilibria. You should notice that we're also seeing things like it does seem like the origin is in fact a source. Everything's moving away. And it does seem so. Anyway, I guess I'm seeing here from this graph, it feels to me like we are. All I was really looking to double check there was that this was going to be a saddle, and this absolutely looks like that saddle type behavior. One line of solutions coming in, one line of solutions moving away. There's our two straight line solutions, one being a sink and one being a source. That is exactly our saddle. So it does look like we properly classified the behavior near 1, 1 to be a saddle by shifting 1, 1 to be at the origin, and then linearizing by discarding higher order terms and classifying using the trace determinant plane. Again, it's hard for us to draw an overall good picture for this thing because that saddle type behavior is only a good description locally. It's only like if you, again, you should be doing this only for all these pictures. It's like if you just look in a small circle around that point, then saddle should be a good classification. Far away, I think it's a bad thing to just say, you're going to see a saddle in this graph because it seems like there's many other things that are going on over here, right? So in general, it seems, and so we're gonna want to generalize right now, but it seems like the graph that we were just coming up with right there, my sort of like short by hand version is we saw equilibria at 0, 0, at 2, 0, and at 0, 3, and at 1, 1 right there, right? What we just saw was that there was equilibria that were moving in towards that 1, 1 along that straight line, things that were moving away from 1, 1 towards the other equilibria along some other lines that are out here. And notice when I say lines, these are certainly curves, but, oh, sorry, oh my gosh, I'm sitting here in the wrong one. There we go. Are certainly curves, but near the near the equilibria, they are closer and closer and closer to looking like straight lines right there. And we certainly saw that these were moving up here and down here and out here and in here. So it seems to me like I can maybe see a better description of what's going to happen to any trajectory in the plane. It seems like if I were to, for example, start at a point out in space right here, that this point is probably going to either come in to this equilibrium right here, or maybe get actually pulled in towards this guy. And similar things over here. If we start in here, I think I'm going to get pulled up a little bit, but probably pulled in towards these ones sitting out here as well. So knowing our classifications of these guys still makes it pretty tough for us to figure out what a diagram looks like. Might be still helpful to have technology out there, but we can do our individual classifications here. And again, our three-step process says convert into a new variable setting based on shifts only, right? This is always just going to be a shift an equilibria to the origin by doing some subtraction or addition from that variable. Once we've shifted it to the origin, we can linearize by discarding the higher order terms, and then use our approximated system, our linearization of the system near the equilibria, to classify using the trace determinant plane and to find a classification of the original equilibria in the untransformed setting. So let's generalize what we did, because here's the deal. We found 4 equilibria here. 3 of them weren't at the origin. I really don't want to have to do all of this every single time. That would be misleading relative to what we saw in chapter 3, that we can trim down a whole bunch of this work. So what we want to do is we want to find a more generic way to do this so that we don't have to do like a mountain of algebra every single time. I hope that's an obvious next step for us here. So we want to generalize this, justify what works in general, clean up the steps so we can do this really quick. And this is going to turn out to be a pretty rapid fire thing despite how much work it sort of takes to just do one up here. So let's look at this in general here. So this is one of those things where you just need to pay really close attention to notation, and we'll arrive at a very satisfying result at the end. So we've been given a very generic system of differential equations. There's no restriction on this really that it's got to be linear or anything. It's just as long as it's a first order planar system. First order meaning one derivative, planing meaning only 2 variables. We're going to identify that there's going to be an equilibria at some location, x naught, y naught. So x naught, y naught is a special location. It's not just an initial condition. I'm saying it's an equilibrium. So this is a special x naught, y naught right here, right? We can always introduce the 2 new variables u and v that will shift the equilibria at x naught, y naught to 0, 0. And you should notice that if x is x naught and if y is y naught, then u being 0 and v being 0 is now our equilibria location. You should also notice that in general, our derivatives are always going to be matching identically between u and x and v and y, because shifting, making just a constant shift is never going to affect what our slopes are going to be. That constant term, the derivative of it just goes to zero. So what we can do is we can use this rewritten version now to rewrite our system. You should notice that dx dt is now du dt, dy dt is now dv dt. We're still using the functions f and g, but in the x slot right here, just like we did before, I added x naught to the other side. So x is equal to u plus x naught, and there's u plus x naught sitting in the x position. Similarly, there's v plus y naught sitting in the y position, and identically just down here for our second setup right here. So this is saying this is our step one. We have shifted the origin, or shifted the equilibria to the origin in terms of u, and we converted the system to uv, where the equilibria that was at some place out in the space is now at 0, 0. Our next step now is to neglect all of those higher order terms. But how do we do this in general and for non-polynomial functions? Textbook has a very nice quote on this one right here. The basic idea of differential calculus is that it's possible to study a function by studying the best linear approximation of that function, saying, just look at the line version of everything. So what we want is we want a linear approximation to a function. And what you should think more generally to yourself is, we want a polynomial approximation for a function of degree 1, a first order polynomial, right? So therefore, what you should be thinking is, we can use a Taylor series of f and of g, and just keep the linear terms. That would be a linearization of it. It turns out that since we're looking in multiple dimensions here, we've got f of x and y, right? This isn't just f of x. If it was f of x, our Taylor polynomial would give us a line for our first order approximation, but we're sort of in three-dimensional space here, so we should be thinking a plane, a three-dimensional plane. You should recognize this general structure right here as being what we get from our Taylor polynomials, right? We get a constant at the given location, and then we get the first derivative. But notice here that you have only ever seen Taylor polynomials in for x and y. Here we have sort of like an x and a y and a z, so there's an additional dimension here. So rather than just getting the initial value, this is sort of, and again, you should be seeing this as like y equals b, initial condition, plus mx. That's just a y equals mx plus b right there is all we're seeing. The only difference for you that you have to identify here is that since we do have an additional variable, we're actually going to get an x term and a y term for each of the degrees of the polynomial that we're arriving at right here. And so very conveniently, for a higher dimensional Taylor polynomial, we're just getting our derivative of f with respect to x and our derivative of f with respect to y as each of the components right here, and we get a linear term associated with each. If you wanted to keep on going, there are an infinite number of higher order terms that are out there. These are all the things that we are neglecting because we're linearizing, right? So let me make sure I'm following my notes along right here. So this is our Taylor polynomial version of this guy right here. And so I just want to point out here that, let's see, oh yeah, I just want to make some swaps that we're seeing right here. So it looks like what this is here is this is really now f of, and we wrote this as u plus x naught, v plus y naught. V plus y naught is really what y is by definition, right? We defined it that way. This is the relationship between v and y right there. That's exactly what I'm holding true down here. Y is the same thing as v plus y naught. You can see that in that equation. You should notice, very, very importantly, that we selected x naught, y naught to be in equilibrium. That means that if you plug in x naught, comma, y naught into the f function, you're going to get 0. By definition, in equilibrium is where dx dt is equal to 0. So this is literally 0 right here. Excuse me. When we say this derivative right here, this is our derivative notation for the partial derivative with respect to x. So I'm going to write this as the partial of f with respect to x times, and this is, by the way, evaluated at x naught, y naught, and this is times x naught, x minus x naught. What is x minus x naught? X minus x naught is just u. Plus the partial derivative of f with respect to y, evaluated at x naught, y naught, times v right there. So it seems like what we've done with this linearization here, and we could do this exact same thing now for g, right? We should now be able to say g of u plus x naught, v plus y naught, is also equal to 0 plus the partial derivative of g with respect to x, x naught, y naught, u, plus partial f, partial y, evaluated at x naught, y naught, times v. Right? So the good news is that we have clearly managed to linearize this thing. You can see that we have no constant term left over, which none of our differential equations in chapter 3 had like a 3 in there, right? They had like a 3x or a 3y, but the constant term is 0 by definition because x naught, y naught by definition was in equilibrium. If you plug it into f or into g, you get 0. We're going to talk partial derivatives in a second. These are easy if you haven't seen them before. And what you should notice is this is basically now of the form AU plus BV equals CU plus DV right there. This is very exactly like what we've been seeing. Right? This is like AU plus BV. This is like DU plus, or sorry, CU plus DV right there, right? So this looks like it's back to being in exactly the format that we wanted it to be. So what this is going to give us now is this is going to give, I mean, I guess that's kind of what I'm saying right here. This gives du dt being partial f partial x times u plus partial f partial y times v, partial f partial x, or partial g partial x, u plus partial g partial y v. All right. Now the good news for this right here is that this is exactly in our format that we're used to seeing this as. So you should notice here that our A matrix is just these partial derivatives all evaluated at that given location. And again, if you haven't seen partial derivatives before, just hang on until we get to an example. There's nothing difficult about this that you're not capable of doing. Technically, partial derivatives are a Calc 3 concept. They're not hard for us to deal with. So don't worry about that. All right, evaluate it, that x naught, y naught right there. So this A matrix seems to be a whole matrix of derivatives right here. So we say that we linearize the system to be, notice that this is back just in our linear setting right here. The derivative of u with respect to t, derivative of v with respect to t. Here's our coefficient matrix A, evaluated at x naught, y naught, times our vector uv right here. So this is our linearized version. So this matrix of partial derivatives that are evaluated at the equilibrium location is referred to as the Jacobian matrix. And now what we can do is we can, so again, think back to our previous example. We had 4 different equilibria. Well, we can compute the general Jacobian matrix that's going to apply to all 4 of them, and then one by one plop in our equilibrium locations as the xy points on this thing right here, and come up with our 4 linearizations sort of all at once, right? That's the beauty of this, is that we're going to find one general Jacobian matrix and then apply all of the equilibrium that we've seen one by one and classify one by one. So that says to me, we don't need to do this substitution over and over and over again to get into our u's and v's. We can do one generic substitution of u being x minus one of the x values of an equilibria, and y minus the y value of that same generic equilibria, until we come up with a general descriptor of it. Then we apply the individual equilibria. The reason that this is different than above is because up here we did very specialty substitutions that only applied to one of the equilibria, the one at 1, 1. So when we do this the specialty case right here, we would have to do all this work for every single one of them. Instead, what we've just realized here is that we're just going to get all of these partial derivatives here that we could one by one apply each of our equilibria. So instead of me just saying it 1,000 times, let's go ahead and do it here. So let's find and classify all the equilibria for this system right here. So step 1 is always going to be to find these equilibria. So I'm thinking we should be seeing a sentence that looks like negative 2x times 1 plus x, right? Is that really the problem there? Oh, nope, it's not. Okay, I was like, I don't remember getting a negative right here. I'm going to change this so it actually matches my notes right here. Negative 2x plus 2x squared. That should be giving me a minus sign in what I just wrote. So x equals 0 or 1. Has to be the case for dx dt to be equal to 0. So for dy dt equals 0 and x equals 0, that's going to leave me with, let's see here, 0 equals y. Okay, so that was easy. That leads me to the equilibria at x was 0, led me to say y must be 0. So 0, 0 seems to be an equilibria. Now if we need dy dt to be equal to 0 and we want x to be equal to 1, then in this case it looks like we're getting a 0 equals negative 3 plus y plus 3. And so it looks like we're getting y to be 0 again. So it looks like x being 1 and y being 0 is also an equilibria. So we've got two equilibria, and one of them is not at the origin here. So we found the two equilibria. Now what we should do is let's find our general Jacobian. So I'm going to kind of write some steps for us here. Next up, let's compute the Jacobian. Now, what we've got to do here is we've got to compute a bunch of partial derivatives, right? So this is going to be our A matrix right here. And what this is going to look like is our partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, and partial of g with respect to y. And by the way, this is pretty easy for me to remember because I know that my matrix is always of the form that the x components are on the left and the y components are on the right. I also know that we always define our differential equations to be f being the top equation and g being the bottom equation, just, I don't know, alphabetical order. And we do have f's on top and g's on bottom right here. So all I've got to do is I've got to think to myself, how do I take a derivative, a partial derivative here? So partial derivatives are just saying, since there's multiple variables out there, we only want to consider one of them to be changing and all of the rest to be constant. So when I do the partial derivative of f with respect to x, that's just saying this is the f expression up here. I want to take the derivative of this expression with respect to x, and we would treat y as a constant if there was any y that's in here. There's no y, so this is just straight up the derivative of f with respect to x. So I should be getting, oh, by the way, I'm going to rewrite something here. I'm not going to call that my A matrix anymore. I'm going to call this my J matrix so that we know it's referring to a Jacobian. Anyway, derivative of the top equation with respect to x, I'm getting negative 2 plus 4x. The partial derivative of f with respect to y, well, the derivative with respect to y holding x constant is 0. Right? And again, partial derivatives say, assume that only one variable is changing and hold all other variables as constants. So when I take the derivative of f with respect to y, treating x as a constant, this is just a big old constant, and the derivative of a constant is 0. Let's do the same thing now for g. The partial derivative of g with respect to x, I'm going to get a negative 3 from the first term. Y is assumed to be constant because we're only taking the partial derivative with respect to x, so that goes to 0, and 3x squared becomes a plus 6x. And finally, we'll take the partial derivative of this guy with respect to y. In that case, negative 3x and 3x squared both go to 0 because x is treated as a constant, and the derivative of y is going to give me 1. So I've now computed my general Jacobian matrix. What I can now do is I can now go ahead and apply the equilibria to each Jacobian and classify. So what we've done by computing the Jacobian is we've come up with a way to generally move any of the equilibria to the origin that we want. We just haven't specified which one yet. So now what I'm going to go ahead and see is that we can evaluate, come on, give me some room here, man. That we can go ahead and evaluate J. And I typically notate this like this. I don't think our book quite notates it like this, but that's okay. The Jacobian matrix as evaluated at 0, 0 is just giving me the matrix negative 2, 0, negative 3, 1. And I can now say, okay, at 0, what's going on? Well, I've got a trace of negative 1. I've got a determinant, let's see, negative 2 minus 0 is just negative 2. And so I can see right away that we're going to get a saddle at 0, 0. And now I can go ahead and evaluate my Jacobian at, what was our other equilibria location? 1, 0. Let's go ahead and evaluate the Jacobian at 1, 0. When I plug in 1 for x here, I'm now getting a positive 2 in the upper left, 0. Plug in 1 for x, I'm now getting a positive 3 down here and a 1. And so now I have a trace of 3. I have a determinant of 2 minus 0. So I now need to do my t squared minus 4d. That's going to be 9 minus 8 is 1, which is positive. So it's real. And now I can see, let's see, so if it's going to be real, I now want to know, is my trace positive or negative? And it's positive, so I think that this is just going to be a source. I was trying to choose between sink center and sink, source, or saddle. It's not a saddle because the determinant was positive. It's a sink or a source. And since my trace is positive, it means this guy's got to be a source at 1, 0. So again, the Jacobian matrix is the thing that's helping us shift our equilibrium to the origin so that it makes sense to consider their linearizations, because it only makes sense to make a local estimate and discard higher order terms if those higher order terms are very close to 0, and they're only close to 0 if the equilibrium that we're looking at is at 0. So one by one, we're moving the equilibrium to the origin and looking close, and then we're moving a different one to the origin and looking close. And the Jacobian matrix is our generic version of any shift that we want. We then, after we compute the Jacobian matrix, say, oh, by the way, I first wanted to do the non-shift of 0, 0. Then I wanted to do the shift the whole system left by 1 to handle the fact that this equilibrium was actually at 1, 0. And so near 1, 0, this is what the linearization of the system would look like. So near 1, 0, I expect to end up seeing some source type behavior right there. We could go and compute some eigenvalues and eigenvectors. I just want to say that here. We could evals of each to get evex of each to help with graphing. So I'm thinking, even if I know that we've got a saddle and a source, I'm thinking like, where are two straight line solutions? Like, how are they oriented in space? Like, even if I know, like, all of these could be a source or a saddle with any of those straight line solutions. So what I really would want is the eigenvectors would tell me where are my straight line solutions, in what direction do they point. And that would really, really help me out with my graph right here. I think we've at least got our classifications. Let's go and check this guy out with technology here, and then we'll look at some slightly more interesting examples. So we just looked at negative 2x minus 2x squared. And plus 2x squared. Same mistake I made a second ago, plus. And our y equation was our negative 3x plus y plus 3x squared. Okay, let's clear all these things right here. What we were expecting to see, let's go ahead and remind ourselves what we just saw. We claimed that there should be a saddle at the origin and that there should be a source at 1, 0. So that's the claim. Saddle at the origin, source at 1, 0. So saddle at the origin. Yep, I'm seeing saddle type stuff at the origin here. I agree with that classification. And it should be a source at 1, 0 here. And I am seeing everything moves away from 1, 0 that's near 1, 0 right here. All of those arrows are pointing away. Now, again, as you get farther and farther away, it's hard for you to look up at this point up here and say, oh, 1, 0 is a source. So remember that these classifications are local only, but we do see that locally there is the saddle at the origin. Locally, everything moves away from 1, 0. We're getting that source type behavior. I don't see any spiraling or any degenerate source or anything like that going on there. So I feel pretty good about those classifications that we just made right there. All right. So in general, our process is find the equilibria using algebra, compute the Jacobian matrix by taking 4 partial derivatives. So you should have x's and y's in your general Jacobian. Then we want to evaluate that Jacobian, just go on down the list of all the equilibria, use your trace determinant plane information to classify with the information that you found at the linearization near that point. Right? So one of the big questions that you should be asking yourself here is this reliable? Since we're making the approximation that higher order terms are negligible, we should anticipate that this will occasionally lead us astray. In particular, one of the things that I think is most useful to note is that a circle is a very good approximation of a spiral. And so this is one of the most common places where we do end up getting some like misleading information from our Jacobian. So let's use our linearization technique to find and classify all the equilibria for the following system. Then let's compare our results to numerically produced graphs. So here's our next system that we want to look at here, and let's kind of recognize that it's going to crop up some issues for us here. So here's the thing that I'm seeing. It looks like with our first so I'm asking first, where are equilibria located? And I guess the thing that I'm seeing here is this. This quantity here is always going to be a positive quantity because it's x squared plus y squared right there. I feel like we're going to need to have, I feel like 0, 0 is the only obvious equilibria that I can identify here. Trying to think of what my algebra argument is as to why I know that there's not another equilibria at the origin or other than the origin right here. Um, and I guess that's, well, right, if x is 0, then y has to be 0. And if y is 0, then x has to be 0 right here. I'm trying to argue for myself that maybe like 1, 1 could work or something like that. And it's because of the wrong signs on these that things like 1, 1 won't work, because the 1, 1 would actually work for dx dt. This is going to be 1 minus, oh no, 1 minus 2, so that's not working out right there. We're going to get just an equilibria for this guy only at the origin right here. So we should also further notice that the linearization, I don't even need the Jacobian for the linearization. Because we don't need to shift any origin, anything to the origin. Let's just go ahead and neglect higher order terms. So what I'm thinking that we're going to get here is that our linearization should look like right? So our linearization, neglecting the higher order terms, well, these are all the higher order terms. X cubed, x times y squared, y times x squared, y cubed. These are all our higher order terms that we're looking at over here. These are all the things that are going to be incredibly tiny if they're near the origin, whereas these are not going to quite be as tiny. These are going to be providing us a bulk of the information about dx dt and dy dt. So that's our good linear estimate of what this system is actually doing. Here's our A matrix then. I can go ahead and compute my trace to be 0. I can compute my determinant to be 0 minus negative 1 is positive 1. I can see that t squared minus 4d is going to be 0 minus 4, which is less than 0, so we're getting complex stuff. And t equals 0 says we're getting a center at 0, 0. So there's my classification based on linearization, is that I'm expecting closed orbit trajectories right here, a center about the origin. So now let's go ahead and then compare our results to numerically produced graphs. So let's go ahead and take a look at, I guess this will be our last example that we see in Bluffton, and then we'll go back to Python for the last one here. So let's go ahead and take a look at this guy over here at Bluffton. So can I, is it going to be cool with me? Can't I just copy and paste this? It would be super cool if I could. Yes, I guess I can. Let's try that again. And our question is, did we really get a center like we were expecting to get. Oh, but I'm sitting here messing around with my window right now. I'll click over momentarily here. So our claim was that near the origin, we were going to be experiencing a center. Is this ever going to update, or am I just... Come on, man. Yeah, I've clicked away. Okay. All right, so here we go. So I've entered in our two equations, and here is what I'm seeing. Oh, and I see what it's going to do to me here. I see. So since I'm not seeing my backwards time trajectories right here, so it seems like what's happening here is we're claiming that we're going to get these closed orbit trajectories near the origin, but so here's the one that I want you to see. Notice where my mouse is right here. Here's what I should do. Let's clear all these curves here. Let's see if I can. That one's even a little bit too close right there. Okay, there we go. With this red one right here, what you can see is I clicked here, and it seems like it is sinking in towards the origin right here. So let's do this. Let's really zoom in right here to actually see this guy. All right. So notice here that as I look at these orbits right here, even that green one, it doesn't really seem like I'm seeing that same, and man, I'm looking pretty dang close to the origin. I mean, I'm starting my XY values at like 0.05, 0.05. Should that not be close enough? And I would argue, yes, that should certainly be close enough. So it doesn't seem like we're actually getting the type of behavior that we were sort of expecting to see right here, and that I'm not seeing any centers show up right here. All right. So I want to, can I copy that image? Yeah. Uh-oh, did I just make a big mistake? I mean, come on, Microsoft Word. Are you joking me with this stuff? I just copy and paste a picture in there and it just goes away forever? Okay, I guess that didn't make any sense. Go ahead and snip this thing and bring it in here. So what I'm saying here is I'm not seeing any closed orbit trajectories, even really, really close to zero. So the question is, why not right here? So one thing we can do is we can look at this in chunks right here. So let me grab our differential equations right here and kind of show you how I'm picturing these guys right here a little bit differently. Why did this not quite work out in this case right here? And then we'll look at one good last example here for our non-polynomial equations, right? So what I'm seeing right here is I want to think about this as being like two different chunks right here. I'm thinking of this as being like a f1 xy plus f2 xy and a g1 xy and a g2 xy. And here's what I'm seeing. If I'm looking at just this first grouping right here, so f1 in this case is like our terms just y and g1 down here. So this is this is actually one of our first examples that we ever saw of our systems here was going to be our when we had the 0, 1, negative 1, 0. Like this guy right here, I think was honestly like the first system that we ever looked at right there. We saw the center, we guessed the sines and the cosines for the solutions. That was like back in chapter 2, right? So that component of it is known periodic. If we just looked at just the y and at just the negative x, that was our linearization. That is works out to be the periodic part. However, if we look at this f2 component here, being the negative x squared plus y squared times x, and the g2 being negative x squared plus y squared y, what you should notice here is that this is always proportional to uh, dx dt equals negative x and dy dt equals negative y, because x squared plus y squared is guaranteed to be constant and, or excuse me, to be positive and the exact same value across both of them. So we're always going to be proportional to this, which is going to give us here a sinc, right? So it seems like in this case here, we ditched the part that said move in or out when we did our linearization, and we kept the part that said do periodic behavior. And when it turns out that this really should have been a spiral sinc overall for the classification right there. So the bottom line is just to say, sometimes when you linearize something and you get a classification of a center, it's actually a spiral source or spiral sinc. In this case, this is actually a spiral sinc right here, right? And I know that it's a sinc because that's proportional to our sinc parts right there. But it seems like what happened here when we did our linearization is we didn't just ditch some parts. We ditched the parts that said move in or move out, and we kept the parts that said just rotate. So our linearization there, we lost all of one type of information and we kept only another type of information, and that caused a bit of a misclassification right there. So it looks like we should have been getting a spiral sinc in this case here. Right. But again, the Jacobian misled us right there. So that's just to say, if you ever use a Jacobian, a linearization technique, and you find that it's a center based on your linearization. If you've neglected some higher order terms, then it's maybe worth going back and taking a second look using some technology to verify that it is in fact a center. And if you see that it seems instead like a spiral sinker source, don't be terribly surprised. Say to yourself, oh yeah, that's something that might happen. When I see the answer of center come out from my linearization process, it's worth a double check is all that's saying right there. So that's kind of our major way in which this can go wrong right here. Most of our other classifications are true to what we're actually going to get here. So let's go ahead and look at one. I think this is our one last example right here. And the important part about this one is that not only is it nonlinear, it's non-polynomial. So we've got a trig term that's incorporated in this as well. We might as well just get a new one for this guy right here. So let's find and classify all our equilibria. This is just our basic description right here. So what I'm seeing here is if dy dt equals 0, then we need to have that y is going to be equal to 0, right? Now if dy dt is going to be equal to 0, with y being equal to 0, then that's going to tell me that we must have that sine of x is going to be equal to 0. And when is that going to occur? Well, that's going to occur when x is 0, pi, 2 pi, etc., etc. Maybe I should just say that this is going to be at pi k is where we're going to get all of those equilibria at, right? So let's say there are infinite equilibria at pi k comma 0. That's our xy locations of all those equilibria that we're seeing out there, right? So let's go ahead and compute our Jacobian matrix. Our general Jacobian. And you should notice here, we clearly have an infinite number of equilibria that we want to classify. However, I hope that you're anticipating, because everything in trig repeats itself, that we should be able to form a general statement rather than literally having to do an infinite number of classifications, right? So let's compute the Jacobian matrix. Remember that this is the partial of f with respect to x, the partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. I'm remembering that we always call this our f equation. We always call that our g equation right there. So what are we going to get for our general Jacobian here? The partial derivative of the f equation with respect to x, well, y is considered a constant, so 0. Partial derivative of f with respect to y, the derivative of y with respect to y is just 1. The partial derivative of g with respect to x, y is considered a constant, so it goes to 0. Negative sine of x is going to become negative cosine of x from the derivative. And finally, the partial derivative of g with respect to y is just going to give us negative 1. Sine of x is considered constant there. Only y is varying, so I'm going to get a negative 1. So here is our general Jacobian for this guy. So let's go ahead and see what we're going to get when we evaluate this guy at some of our equilibria. So I'm thinking let's do the easiest one first, which is the one that's at the origin here. The Jacobian that's at the origin right here, we should be getting 0, 1, negative 1, negative 1. And when I do this, we should be finding our trace to be negative 1. Our determinant is 0 minus negative 1, which is positive 1. T squared minus 4d is going to be 1 minus 4, which is less than 0, so we're complex. Our t is negative, so I'm thinking a spiral sink. Now, what's happening at the next one here? Our next one would be at pi, comma, 0. And here I can see that we're going to get a 0, a 1. Now when I plug in pi here, we get negative 1 from cosine, so we're actually going to get a positive 1 in that lower left. Here my trace is still negative 1, but now my determinant is also negative 1 because we're getting 0 minus 1. And so now I'm seeing here that because my determinant is negative, we're just getting a saddle at pi 0. Excuse me. And so here's the next thing I'm thinking. Our next one would be at 2 pi 0, but this should just be the same thing as we got at 0, 0, because cosine is 2 pi periodic. So I think that I can generalize this as saying we're going to get spiral sinks at, and what are we saying here? It's going to be at 0 and then 2 pi and then 4 pi. So I might call this 2 pi k 0. And we're going to get a saddle at every, and this is all of our odd ones of it right here. So I'm thinking something like, why am I being dumb right here? I just want to get, so if, yeah, it should just be two k plus 1 pi. There we go. Now I'm done being dumb right there. Now whenever you plug in a k value, an integer for k, you're always going to get an odd number for that one, right? So even multiples of pi, odd multiples of pi. So our issue with this one, and the reason why this is our good last example right here, is just because I can identify that this is what's happening doesn't mean it's easy for me to draw the picture here, right? So if I'm trying to draw this picture, I'm thinking here we are at 0, 0, pi, 2 pi, negative 2 pi. Well, what the heck's going on right here? I'm thinking to myself that we are having some spirals, for example, a spiral sink at the origin right here. But then I need to have like a saddle right here. That seems, I mean, I feel like if I'm going to have a saddle here, it seems like there must be some like going in to kind of agree with this one here. And therefore that would be like our inward facing one. But then this would have to be our outward facing one, I guess, right here. And that seems to agree with the fact that I'm expecting to see another spiral sink that's happening over here at 2 pi, right? So I guess this still seems very, very confusing to me as to how this is going to work. I do see over here, though, it does seem to make sense that I might have some like saddle arm, like being the connector that's going on out there. Something like this. This feels plausible to me, I guess. Right, more spiral sinks going on right there. Maybe? It's a very tough picture to figure out how to draw. So even with classifications, I guess I say it down here. I'm just going to go ahead and backspace that. So what I want to do is I do want to use technology to take a look at this picture. It's tough to complete this picture by hand. Even if we can get all the correct classifications from our Jacobian matrix, sometimes we still need help making this picture, even if we have all the information. So we had an infinite number of equilibria. We technically were able to classify all of them like mathematically. And look at how like this didn't really take that much work. We literally just classified an infinite number of equilibria on one screen right here. That wasn't that bad. But this picture is still kind of confusing, like how is this actually going to work out here, right? So let's go ahead and wrap this up by taking a look at this guy with some Python stuff right here. And here's my issue. What I really want is I really want to get a whole bunch of equilibria here. I don't just want a box grid of them around the origin. I want to have a much longer box grid of them that's going to stretch out through this whole thing, right? So I maybe want like one here, one here, one here, 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 something like that. I want a whole grid of these things. So what I'm going to do is I'm going to do a slightly different way of making my initial conditions here. So what I'm going to do is this. I made a different initial condition list for this one here. I'm going to get rid of our old one, comment that one out, and here's what this is going to do. The initial condition list, I'm going to build this instead of explicitly writing out the list, like I literally listed all the ordered pairs right there. I'm instead going to do a list comprehension where we describe the list to Python. So it's in brackets, so that's how we know it's a list. What are the objects that I want in the list? Well, they should all look like an ordered pair XY. Where am I going to get the values of XY from? Well, it's going to be for every X value in the range from -8 to 9. Remember that the range function in Python includes the lower bound, but discludes the upper bound. So this will actually give me all X values from -8 to 8. And then all Y values, it'll really be from -2 to 3 right there. So this is going to give me sort of like a mesh grid of points with all of the X values possible and all of the Y values possible. You'll be able to see it in our graph down below. The other thing is that I need to switch examples right here. So I'm going to comment out that stuff, and I'm going to uncomment this stuff. Remember that if you're trying to follow along here, remember that the sine function is not native to Python. I had to ask NumPy to give me its version of sine right there. So now that I've got my smart initial condition, whole grid of initial conditions out there, and I've got my correct function, let's run this bad boy here and see what we end up with. I'm remembering one thing right away, which is that I think I want back this graphing window right here. All right, so here is what you hopefully find to be now. That picture, don't look at that picture right there. But here, I'm finding a pretty satisfying picture, and here's what I can see. So look carefully at this one here. One, I can very clearly see these spiral sinks happening right here. I know that there's sinks because my solid lines are forwards time. So from these like sets of green dots around here, it seems like the solid lines are all towards the middle. So we're sinking towards the middle here. All the dashed lines are far away. That's all of our far away stuff. The other thing, very importantly, that I can see is looking right here. Right here, you can see this kink happening right here. You can see another kink happening right here. That's our good indication that we're looking at a saddle to where we're on near one of our inward trajectories, but that it wasn't the perfect straight line that went in, and so it had to dip away at the last second to agree with the outward traveling trajectory right here. So I absolutely see some spirals and some sinks being generated right here. They seem to be at about exactly where I anticipated them being. So this picture very much agrees. And by the way, you can see all these green dots. This is the green mesh grid of dots that I created by using that list comprehension for our initial conditions up above. So this picture, I think, does a good job of justifying exactly what we were seeing, and maybe the slightly bigger version is maybe a little bit nicer for us to actually look at right here. But this is a kind of our, we do see the spirals and we do see the saddles occurring right there. I can even see it. This is right at pi right there for that saddle. I can see it's about a negative pi for that one, about a positive pi for that one. So this picture does agree, but like I can't draw this picture by hand necessarily. And so the exciting thing I want to tell you for our last component of this is that this system of differential equations right here is actually modeling a real world phenomenon, which is that I believe that this is the one, or maybe this is ever so slightly adjusted. I feel like I should post this the link to this video, but 3 Blue 1 Brown in his descriptions of differential equations, he starts with this description just of a system of a pendulum, where if you give a pendulum enough of an initial condition, it will just do a bunch of of cycling around, but eventually it can't make it around for another lap, and it just settles down to the origin at the equilibrium at the origin right there. That's exactly what we're seeing some trajectories doing here. Okay, this one's going to be a little bit different because we're not getting some trig waves up top right here. We're getting saddles instead, but still closely related to a physical system involving a pendulum right here. So maybe I'll link that 3 blue 1 brown video as well, so you guys can take a look at that, guys. So here is our linearization to handle equilibria that are not at the origin right here. In general, you need to just be able to handle taking a couple quick easy derivatives right here, partial derivatives to compute your general Jacobian matrix. From the general Jacobian matrix, we're going to get our linearizations of our systems near those equilibrium and saying, if you only look in this little spot around that equilibrium, then it should look like this type of behavior. But if you look far away, it might not be, but that's fine. We just want our local classifications here. And by doing this, we're able to classify any equilibria sitting at any location, regardless of the setting that we find our differential equations to be in right here. Drawing our pictures might be within our capabilities, might not be, but you should at least be able to take your by hand drawings and realize that they're in some way, shape, or form agreeing with the technology drawings that you're getting right here. So that wraps it up for me here today on section 5.1. Next week, we're going to look at second order differential equations and see what happens if we have some funky terms in there. Just like here, we're expecting from chapter 3 to only see things like ax, by, cx, dy, and no other terms. Today, we handled incorporating other types of terms, right? Higher order terms, trig terms, stuff like that. In 4.1.4.2, we're going to do a similar thing, but for second order differential equations, where before we did like ax double prime plus bx prime plus cx equals 0. Well, now we're going to say, what if it's instead equal to like sine of t on the other side? That'll be our sinusoidal forcing. That'll be in 4.2. Finally, we're going to wrap up this class by finally making a legitimate return to doing calculus in chapter 6. You should think about how little calculus we've actually done here this semester. I feel like half the reason people are so upset about partial derivatives in this section isn't because they didn't take Calc 3, it's because you haven't taken a derivative in like a year and a half at this point. So remember that you need to be able to take derivatives here, nothing too crazy. So that wraps it up for me for section 5.1. I'm going to see you guys for our overlook of chapter 4 next week, and then for chapter 6 the week following that, and then I'll wrap up the course here. Have a good one, everybody.